weathering. In this video, we're going to be looking at an introduction to waves, and this is video 1 of 4 for our waves topic, so let's crack on. Waves are a fundamental piece of the physics puzzle. They make up a large proportion of energy transfer, and they pose significant problems to engineers when designing buildings, to musicians creating audio, and to those who are studying earthquakes. There are natural waves like seismic waves from earthquakes and electromagnetic waves like light, and there are man-made waves like the sound from plucking a guitar string. There are two types of wave that you need to know. There are transverse waves and there are longitudinal waves. In a transverse wave, vibrations move up and down and travel along the medium. The medium is just the thing that the wave is travelling through. It could be air, it could be a spring, or it could be a wire. In a longitudinal wave, the vibrations move forwards and backwards and travel along the medium. And this is exactly what I mean by transverse and longitudinal waves. You can see from the animation that the top wave is a transverse wave. The vibrations in this wave are up and down, whereas the direction of energy transfer is left to right. Below, or the longitudinal wave, you can see that again the direction of energy transfer is left to right, but this time the oscillations are the same direction, left and right. The way waves travel is called the propagation of the wave. We say that in a transverse wave, the wave oscillations are perpendicular or at right angles to the direction of energy transfer. We say that in a longitudinal wave, the wave oscillations are parallel to the direction of energy transfer. And you can remember which one is which by remembering this little word here. And this word is taralap. Taralap stands for transverse are right angled, longitudinal are parallel. And oscillations just mean the direction which the particles vibrate in. Remember that waves cause particles to vibrate. So, longitudinal waves have regions of compression and regions of rarefaction. Compression is where particles are squeezed together, and rarefaction is where they're split up. So you can see here that we'll have regions where the particles are all bunched up together, and regions where there are large gaps between the particles. These regions are called compression and rarefaction. Sound waves are an example of a longitudinal wave. Sound causes air particles to compress together, and then these compressions pass through to the next particles, and a chain reaction is set up. Particles keep hitting each other, and the sound wave travels through the air. Transverse waves have regions where the displacement of the medium is above, and regions where it is below. The dotted line on this diagram here shows the wave's resting position, and the resting position is just the medium without a wave. So you can see that there's parts of the wave where the displacement is above the resting position, and there's parts of the wave where the displacement is below the resting position. Water or sea waves are an example of a transverse wave, and so is light. Sea waves are the movement of water particles up and down and are caused by winds in the oceans. Now this next bit's really important. Waves do not move matter. The matter oscillates, but does not actually move along the direction of energy transfer. Instead, waves themselves move. They move through the medium. This can be illustrated with a water wave moving through a ripple tank and a ball floating on top of it. The ball will stay in the same place and will not move in the direction of energy transfer. We're going to watch a little video now. Hello there. We're looking at the propagation of waves. Waves have energy, whether that is seismic waves making the earth shake during an earthquake, water waves, or the waves which carry sound. Waves transfer energy from one place to another. If you look at the wave side on, you will see the movement of particles either up and down or left and right, depending on if the wave is transverse or longitudinal. The top shows a transverse wave, and the bottom a longitudinal wave. Remember, it is the wave which travels, not the actual matter inside the medium, We can see in this animation, if we concentrate on one particle, that it moves up and down. The particles do not move with the wave, only the wave moves in the direction which it is travelling, not the actual matter. If you're following along in your revision workbook, pause the video now and complete task number 1. Next, we're going to have a look at properties of waves. In order to look at properties of waves, we'll need to have a picture of a wave. So here is a picture of a wave. Firstly, we're going to have a look at the amplitude. The amplitude of a wave is the maximum displacement of the medium from the rest position. Amplitude is measured in meters. The wavelength is the length of one wave from the same point on each wave. Wavelength is measured in meters. Next, we're going to have a look at wave speed. The wave speed is the speed in which the wave is moving through the medium. Wave speed is measured in meters per second. Next is frequency. The frequency is the amount of waves passing a point each second. Frequency is measured in hertz. 1 hertz is the same as 1 per second. The amount of waves passing this point in 1 second is 1. Therefore, the frequency is 1 hertz. The period of a wave is the amount of time it takes for one full wave to pass a particular point. We measure this in seconds. For example, if it took a wave 30 seconds to pass a point, then the period would be 30 seconds. Period and frequency are related to each other. They are inversely proportional. This equation is the first equation which you need to know how to apply in the waves topic. Period is equal to 1 over frequency, where period is measured in seconds and frequency is measured in hertz. So the first equation which you need to apply in waves is time period is 1 over frequency. You don't need to worry about remembering this one. It is given on your formula sheet, but you still need to know how to use it. So let's do a worked example. The frequency of a sound wave is 30 Hz. Calculate the period of the sound wave. Okay, well firstly let's write out our formula. Period is 1 over frequency. We know that the frequency of the wave is 30 Hz, so we can write that the time period is 1 over 30. Well, 1 over 30 is the same as 0.033. Since time period is measured in seconds, our final answer is 0.033 seconds. If you're following along in your revision workbook, pause the video now and complete task number 2. So, can you identify wavelength and amplitude? Which of the following of these are wavelengths? Well, let's have a little look. The orange, the purple and the green arrow are wavelengths. They are all one full wave from one point to the equivalent point on the next wave. So you can see here we're on a peak of one wave and here we're on the peak of the next wave. So one wavelength is just the distance between those same points. Here we're about halfway between the peak and the medium, and here we're also about halfway between the peak and the resting position. So that means the distance between these points is again one wavelength. And exactly the same can be said for this green length here. So which of the following are amplitudes? The orange and the red one are. And that's because they are all the maximum displacement of the wave. The wave doesn't go any further away from the rest position than at these points. So here we are on the peak of a wave, and here we're on the trough of a wave. And these are both the maximum displacement from the resting position. So the distance from here to the resting position is the amplitude. The most important formula which you will learn in this topic links frequency wave speed and wavelength, and that formula is wave speed is equal to frequency times wavelength. So this one you do need to know, it isn't given to you on the formula sheet. Wave speed is measured in meters per second, frequency is measured in hertz, and wavelength is measured in meters. The velocity of the wave is measured in meters per second, the frequency is measured in hertz, and the hertz is just times per second. So 5 hertz would be 5 waves per second, and wavelength is measured in meters. A wave speed is found to be 12 meters per second. If the frequency of the wave is 7 hertz, what is the wavelength? Well, firstly we're going to write down our wave equation. Wave speed is equal to frequency times wavelength. We know that the wave speed is 12 meters per second and the frequency is 7 hertz, so we can plug this into our equation. We want to find the wavelength, so let's divide both sides of the equation by 7 to get wavelength on its own, and if we divide 12 by 7 we'll get 1.71. Wavelength is measured in meters, so our final answer is 1.71 meters. So you can actually measure the speed of sound waves quite simply. All you need to do is get 2 people. We'll call these people person A and person B. Get these 2 people to stand 100 meters apart. Person A fires a gun, a starting gun, as we don't want any casualties, and person B times how long it takes between them seeing the gun being fired and the sound arriving. When you have a distance, you can divide this by time, and then you have a speed. As speed is equal to distance over time. Now we're going to watch a small video. Hello there. We're going to be measuring the properties of waves using a ripple tank. With a ripple tank, you can work out the wavelength and frequency of waves in water. A ripple tank is a tank with a glass bottom, a light, and a vibrating dipper connected to a power pack. The idea of a ripple tank is to project ripples or wave fronts onto the surface, often paper, below to be recorded. In order to measure the wavelength, we place a meter rule by the paper. Then we use a camera to take a picture of the paper with the ripples present. We can then look at the photograph and measure the distance of 10 waves. Dividing this distance by 10 will get us an accurate measurement for the wavelength of one wave. As well as the wavelength, the frequency can also be measured. To work out the frequency, we use a similar setup to before, except this time we take a video recording of the waves. Record the waves travelling along the column of water and pick a point. Count the amount of times waves pass this point in a certain amount of time, say 10 seconds, and then use this formula. If you need to work out the wave speed, then you can use the wave equation which we already know. And that is how you work out the wavelength, frequency and wave speed of waves in a ripple tank. Okay, so if you're following along in your revision workbook, now it's time to do task number 3. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.